Good late morning, everybody. I'm Jonathan Jennings, meteorologist with the Division of Water Resources, where my primary task is managing and overseeing the state's cloud seeding program. Before we get into what cloud seeding is, I always like to bring up this 2003 report from the National Academy of Sciences, and the quote that states, "The committee emphasizes that weather modification should be viewed as a fundamental and legitimate element of the atmospheric sciences." A lot of what we know about cloud microphysics comes from early cloud seeding weather research, which is very important in our numerical forecast models, which is vital to weather forecasting in general. So I just want to start off with this and let everybody understand that cloud seeding is a real science and something that has been ongoing since the 1940s. All right, so what is cloud seeding? Well, really simply, it's the act of introducing favorable nuclei into an already precipitating cloud to promote cloud droplet growth and ice nucleation. So in the state of Utah, we have two primary methods of cloud seeding. And first is our traditional technology, which is use of ground-based generators, which relies on the orographic winds transporting material up and over the mountain ranges into the favorable parts of our storms. And then the second is through drones. And drones allow us to be more precise with the targeting, getting directly into the cloud layer that we need and releasing the material right in those precise locations. But ultimately, what we're trying to do here is interact with very small supercooled liquid water droplets. So these are droplets below the freezing level that don't have the surface area or surface tension to freeze, and they don't have the ice nuclei to attach to. So we release silver iodide into the cloud, which is structurally very similar to an ice crystal, and upon contact, we allow those supercooled liquid water droplets to freeze, allowing them to grow more efficiently and then ultimately leading into additional precipitation. So silver iodide could be a scary term primarily because of silver. And silver alone, that free silver ion, does have negative effects in the environmental impact. However, silver and iodide have a very strong covalent bond, which allows it to stay in a solid form, which is great for two reasons. One, we're releasing these silver iodide particles into supersaturated environments, so we want it to stay in that solid form. But also, when it gets onto the ground, we want it to stay in a solid form so it's not bioavailable. With that strong covalent bond, the maximum solubility of silver off of silver iodide is 0.984 micrograms per liter. So that's parts per trillion. And there's been studies in California, Idaho, Australia, all over across the U.S. that show that silver iodide has no environmental impacts when it comes to cloud seeding. We took it a step further and we wanted to do a research project here in our backyard that is ongoing right now. And the preliminary analysis is showing 0.012 micrograms per liter. And all the silver we're finding has lead attached to it, meaning it's coming from erosion from our mines. We've yet to be able to find any silver coming from the silver iodide cloud seeding program. I'm surprised no one's talked about this yet, but why do we cloud seed? Well, big part of it is 95% of our water resources is derived from our winter snowpack, but also climate variability is just part of nature here in Utah, but it's also just getting worse. And I think the last 3 years have really shown that. 2023 to what just happened this past winter, those extremes are likely to be ongoing. So here we're looking at the snow water equivalent across the Great Salt Lake Basin. That's showing how much liquid water is inside our snowpack. But we're also seeing a negative decadal trend. So these are the different decadal periods, and the 2020s and 2010s are far below what we saw the previous 3 decades. So this is unfortunate and probably something that's going to continue. But also another factor that's really important is when is our peak SWE occurring, and how does that impact our runoff efficiency? We're losing 3.2 days of our peak SWE per decade, and that's probably going to only amplify, and that's something we saw this year. The Great Salt Lake Basin typically peaks around April 3rd. This year it peaked on March 9th. So that's really unfortunate when it comes to runoff efficiency. So Utah has a very strong regulatory framework around our cloud seeding program. This ensures that operators are doing their part to conduct a very good operation. We require a permit, which is a 3-week public notice of detention, proof of liability insurance, operations plan with embedded suspension criteria. So when is our SWE getting towards that 95th percentile for runoff in the spring, but also avalanche considerations as well. And then we also require license, which really just vets the operator and make sure that the meteorologists are qualified to operate. We have three permit holders right now: Rainmaker Technology Corporation, Rain Enhancement Technologies, and then Emory Water Conservancy District. Rainmaker is part of North America Weather Consultants, which has been our legacy partner since the mid-'70s. So here's a look at our target area. The map on the right basically gives you a really good idea of where we're working. All those little triangles are where some of our ground-based generators are. So you can see we're not biasing towards one area versus another. I think that's a misconception about Utah's cloud seeding program. And then those hash areas are where some of our drone teams were this past year. We're going to move those around a little bit based on local participation. We also have the very big Bear River Basin cloud seeding program, which is jointly funded by the state of Idaho and the state of Utah. This past year, we had 40 drones operating in that area. We learned a lot from that program, especially when it comes to drones and targeting, and we were able to see seeding signatures, which indicates that our silver iodide is indeed turning supercooled liquid water into snow. This year's focus is going to be on that dark blue area in the Bear River Range, where roughly 3 to 3.5 million acre feet of water is produced from the snowpack. Another big question is robbing Peter to pay Paul. A cloud has 100% moisture within it. Only 9% of that moisture is actually precipitated out. So if we're increasing precipitation by just 10%, we're only taking 9.9% of the total moisture now in terms of precipitation. But also, a cloud is an open system. So as water depletes, as long as moisture advection is occurring, it's going to continue to replenish itself. Another thing that we need to consider, too, is the latent heat transfer. So when we go from a supercooled liquid water to an ice crystal, or even from a water vapor gas to an ice crystal, a lot of heat is released into the cloud. And just like a hot air balloon, if you add heat to it, the cloud grows more robust, lasts longer, and results in what we call extra area benefits. So we're actually seeing positive increases of precipitation further downstream from our target areas. So the idea of robbing Peter to pay Paul is completely false. All right, now the toughest thing I think that we deal with is the evaluations. Historically, in the state of Utah, we've done target and control evaluations of highly correlated snow-tell sites measuring that SWE. And then we run linear regression models, and we've showed about a 6 to 12% increase since the mid-'70s. Water Resources back in 2018 did a analysis showcasing that we're producing about 200,000 acre feet of additional stream flow. Other programs are in that 10 to 15% range, but of course, there's a lot of issues with this. Snow redistribution, the fact that it's a point measurement, and those correlations could be more strongly related to the atmospheric processes like El Nino and La Nina. So what we've done is this past year, we've done Snowscape. So Snowscape was a research project jointly collaborated with the University of Utah and Utah State. We took all these different atmospheric observations, sent it off to the National Center for Atmospheric Research, where they're doing a calibration of the WRF weather mod and WRF hydro forecast models, and we're able to simulate what's occurring within our cloud seeding programs. And that could lead to a better idea of how our targeting and control evaluations have taken place over the years. It was a huge effort, and I can't thank the University of Utah enough for their participation in this. We had gap-filling weather radars, radiometers, solometers, and a bunch of other instruments that you guys could ask about later. So I think the whole idea here is how to get you guys involved. I think a big one is advocacy. Champion evidence-based cloud seeding with the legislature. We have a lot of legislative support, but it's never a bad thing to continue educating. Help counter misinformation. I think this is a huge issue that we deal with in cloud seeding. And then frame cloud seeding as a critical tool for water resources in the West. It is not the tool. It's just one of the tools on our tool belt. And then education is key. And it's not just educating others, but educate yourselves. Reach out. I love talking about cloud seeding. I'll tell you everything there is to know about it. So reach out, understand what the capabilities are and what the limitations are, because there are both. And then help us connect with those hard-to-reach audiences, especially out in those rural communities. And then another thing, quite not exactly related to cloud seeding, but build community awareness in the critical gaps in our weather observation network. We have very, very poor weather radar data, and our MesoWest program is about to get overtaken by Synoptic. That's going to require funding for that. So help us build those connections, and that's all I have for you now. Thank you so much.